Hello and welcome to Void Electronics. As you can see in this video, I've made some huge progress with the video to scope project, and it was quite a journey, so I think it deserves a follow-up video. The solution to the issues that I have had in the previous video were pretty challenging, and they involved designing a video amplifier, simulating it in LT-Spice, and also designing a quick and dirty deflection amplifier. So let's get started. So let me show you how I got from this to this. In the previous video I used the Tektronix 466, and this is pretty much all I managed to get out of it. The picture is really dim, and even the blank raster looks dim, so I don't think there is much we can do about it. This is maybe due to a weak CRT or something like that. So this is what the blank raster looks like. I know it's pretty bright on camera, but in reality you can barely see it, and when you enable the modulation the picture is even dimmer, so this is a dead end. One more thing before moving on, this is a storage CRT, so we can put it in storage mode and we will get some really freaky effects. This also intensifies the image, by the way. So yeah, this is really fun. Look at this. I think this is so trippy. We can play with adjustments just a little bit, and maybe we'll get something more meaningful. Maybe not. So yeah, it's really hard to adjust it, but it's a lot brighter if you can deal with this lag. That is. In an attempt to fix all these issues, I decided to try out this Tektronix 515A, and this turned out to be an analog electronics rabbit hole. Let me show you why. So let's put it in XY mode and see what we get. Okay, so this controls the horizontal size when you are in XY mode, and we already have something here. Let's see if we can center it. And this is pretty much all that we can get out of it at this point. So the image is in some ways just a little bit better. First of all, it can get a lot brighter, which is nice. It's really low contrast, but we'll get to that later. And I think it even looks sharper. So the initial results are really good. However, there is no way to make it wider than this, so it's really distorted. Or we can adjust it by doing something like this, and then it's obviously very small. So let's see how to fix all these issues, because now we have even more issues to fix. To fix this, I think you can get away with a simple amplifier based on an op-amp, but we need to do some tests first. First of all, we need to look at the signal that comes out of our video to scope converter board. So this signal is 2.4 volts peak to peak with a peak voltage of 7.6 volts. Now we need to determine the required amplitude in order to get full deflection on this oscilloscope. So to do that, I connected the oscilloscope to a DC power supply, and the DC power supply is connected to the external horizontal input. So let's see what we get. The power supply is now off, and we need to center this line onto the screen. Is right in the center, so let's turn on the power supply and see what voltage takes us right at the edge of our display. Okay, we are increasing the voltage, and here we need around 5.6 volts. 5.6 volts takes us to the last vertical graticule. Let's invert the polarity and see what we get. I hope it's symmetrical. It's almost symmetrical, so we need around 13 volts peak to peak in order to get full deflection, I think. So as the Mythbusters would say, it's back to the drawing board. Let's design a quick inverting amplifier using an op-amp. So here we have the op-amp. we need a feedback resistor right here, and we need an input resistor right here. Let's call this R1, let's call this R2. This is where our input will be, and this is where the output will be. So as you noticed before, our signal has an offset, and we need to sort of cancel it out. And to do this, I'm going to use symmetrical power supply. So we will power this up using plus and minus 9 volts out of some 9 volt batteries. So let's call this VCC plus and VCC minus. And to cancel out the offset, we can do some tricks here instead of connecting the non-inverting input to ground. So instead of doing that, what we can do is we can apply an adjustable voltage on that input, and then we can cancel out the offset, sort of. So to do this, I'm going to use a trim pot. Let's say this is a 100K, and we can connect it between VCC plus and VCC minus, and this will give us an adjustable voltage between minus 9 volts and plus 9 volts that we can then apply to the non-inverting input of this amplifier. And now we need to calculate the gain that we need. So we have 13 volts peak to peak that we need at the output in order to get full deflection on the CRT, and we need to divide that by what we currently have at the output of our circuit, which is around 2.4 volts peak to peak. So this gives us a required gain of around 5.41, and I think we can round this up to 5.6 in order to take advantage of common resistor values. So to do this, first of all, we need the expression for the gain. So assuming that this is an inverting amplifier, the gain would be R1, actually minus R1 divided by R2. So we can choose a value of 10K for R2, which is a reasonable value, I guess. And then we can calculate R1 based on that, and since we are aiming for a gain of 5.6, this needs to be 5.6 times larger, so this would give us 56K. And that's about it. Here we have our amplifier. One more thing, this will saturate the amplifier, so this adjustment is not the best. Maybe it would benefit from some extra resistors here, but let's just keep it simple like this and see if it works or not. By the way, if you're interested into more boring theory and you want the full output expression based on all these, we can do some quick analysis here. So for the inverting amplifier, assuming that this is the input and this is the output, the expression is pretty simple. So V out is minus V in multiplied by R1 divided by R2, so something like this. However, if we look at this and we think of this as another input into our circuit, this suddenly looks like a non-inverting amplifier. So this has a different gain, and this will be amplified, by the way, just like this signal. So if you have 1 volt here, this doesn't mean that you get 1 volt at the output, so it will amplify the offset as well, because here the formula for the non-inverting amplifier applies. So V out in this case is, let's call it V offset, and it would be V offset multiplied by 1 plus R1 over R2. So obviously, since we have two inputs here, the total output is actually the sum of these two. So at the output we will get minus V in multiplied by R1 over R2, and to this we have to superimpose the voltage actually the voltage here amplified by the non-inverting amplifier formula. So plus V offset multiplied by 1 plus R1 over R2. So this is why this will quickly saturate the amplifier, so it will be a really touchy adjustment unless we do something about it. Here's the circuit on a breadboard along with some other things. So it's powered by these two 9-volt batteries. This is the positive 9-volt rail and this is the negative 9-volt rail. They go straight to this op-amp, which is an NE5532. And these are the feedback resistors. They are 100k each and they are in parallel for 50k resistance. It's all I could find in my junk box. And this is the input resistor, which is a 10k resistor. And in order to adjust the offset, here's the 100k pot that is once again connected between the positive rail and the negative rail, and the wiper goes to the non-inverting input. However, if you look closely here, you will see some extra things, and that's because I decided to use buffer at the input of this circuit in order to keep the ramp generators going. So actually this is not needed for the horizontal section, but I wanted to experiment with this because I want to build something similar for the vertical as well. The horizontal already has some buffers and an amplifier after the ramp generator. However, the vertical as it is goes straight to the BNC connector, which means that it's really sensitive and it needs a buffer if you need to do anything else with it. So this circuit has an input impedance of around 10k because after the 10k resistor you have a virtual ground. So you need a buffer if you want to connect this directly to the ramp generators. And the buffer is just classic emitter follower with a load resistor. So the load resistor is a weird value here. It's 6.81k because that's what I could find around here. And we also have a resistor, a base resistor, which is 220 ohms to keep this from oscillating. And there is one more thing here. We have a 1 meg pot at the input of this buffer so that we can adjust the horizontal size. Let's see if this works. I connected it to the scope, so let's see what we get. Okay, we get a line. Nice. And now let's see if we can adjust it. Yes, it works. So by adjusting the offset, we can take this line all the way to the right and all the way to the left. So I think this works. Now let's increase the gain basically by adjusting the input pot. Oh, we have something here. It goes off screen, so we need to compensate it from the offset. We definitely have a picture here. Yeah, more gain and more offset, more gain and more offset, and so on. And by repeating this, I think we can cover the entire screen. Let's see. Yes, this is so nice. So here it is. We are covering the entire screen now, but the picture is really dim as expected. We need an amplitude here that's a lot higher on the beam modulation. So yeah, this is it. We get a full raster, but we need to do something about the contrast as well, unfortunately. So we are far from done. This low contrast means that the amplitude of the video signal is way too small for this oscilloscope. So guess what? We need another amplifier. Let's see if we can do that too. As you can see, we have plenty of brightness here, but as soon as we crank the intensity up, we lose the picture. So I think this has potential. So assuming that we give it a higher amplitude, I think we will get a really nice picture. let's see if we can fix this as well. Designing such an amplifier will be quite a challenge because it needs to be high bandwidth, so it needs to have a bandwidth of around 10 MHz. It needs to have a gain of around 10, and that's because I think you can get around 5 volts peak to peak out of our board, and our target would be to reach 50 volts peak to peak or something like that, which implies that the transistor also needs to be high voltage. So we need something that can take at least 200 volts collector to emitter. And I think I have some transistors that fit this purpose here in my transistor collection, which are transistors belonging to the BF series. These transistors were, some of these were, let's say, output transistors for CRT TVs, so they should do the trick because this is exactly what we're trying to do. We're trying to drive a CRT here, so yeah, look at this. They don't make them like that anymore, do they? This could work, but I don't want to open the box. Let's see if we can find something else here. Maybe this, who knows, or maybe these ones, BF 871. I think these are perfect for what we're trying to build. You may be wondering why I went for a transistor amplifier instead of a dedicated IC, and here's why. So you can find some video amplifiers that have enough bandwidth, but they cannot swing to such a high voltage, or you can find high voltage amplifiers that cost a fortune, and they only have a bandwidth, a gain bandwidth product of around 4 kHz. So I couldn't find a single IC that can both swing high voltage and have a high enough bandwidth. And remember that we are looking for a gain bandwidth product of at least 100 MHz. So I decided to go for a discrete transistor amplifier. Now, when it comes to choosing the proper transistor for this, the process is more involved than it looks on camera, because honestly, off camera I had a look at the data sheets of all the transistors in my collection that seem to fit the purpose. So it's a little bit more complicated than picking out a transistor at random out of the BF series. So here's why I think the BF 871 would work. First of all, looking at VCEO, which is the collector emitter voltage, this is a maximum of 300 volts, so I think this is more than enough for what we're trying to do here. And I also had a look at the transition frequency, because this is equivalent to the gain bandwidth product or something like that. So since we are aiming for a bandwidth of 10 MHz and a gain of 10, we need a transition frequency to be at least 100 MHz. Unfortunately, the minimum transition frequency for this transistor is 60 MHz, but I think we can live with this. With all these parameters in mind, let's design our amplifier. My plan is to keep things simple and to use a common emitter topology and just give it a try and see if it works. So this is based on an NPN bipolar transistor. We have an emitter resistor right here, a collector resistor right here. This goes up to VCC. This is grounded. Here in the base we have a series resistor to keep it from oscillating, so this should prevent parasitic oscillations. And then we need our bias network, which once again consists of two resistors. This one goes up to VCC, and we have another resistor that goes to ground, like so. And now we have to choose the values for all these resistors, and maybe it looks complicated, but it's not really all that complicated. So first of all, actually, let's draw the input and the output here. So in order to couple our signal into it, we need a coupling capacitor, and I think a value of 1 microfarad is good enough. Of course, you can do the math here, because this forms a low-pass filter, so you can go wild with that. And I'm not in the mood for doing that today. I will hope that it just works. So anyway, this is the input and this is the output. Okay, so in order to keep things simple, we need to choose the collector current for this transistor, which is once again based on experience or based on some data that you can find in the data sheet. In my case, I noticed that this transistor is characterized at 10 milliamps, so I will go with 10 milliamps and see where we go from that. So IC, or the collector current, will be 10 milliamps. This helps already to set a few parameters here. And then we want this output to swing equally between the positive rail and ground, and in our case VCC is 100 volts. Once again, this is a value that I chose in an attempt to get 50 volts peak to peak at the output. We need some margin here because the collector will not be able to approach any of the power rails actually. So since we have 100 volts here, if we want this output to be able to swing equally between the rails, we need this to be at 50 volts. So this node here, or VC, let's call it VC, will be at 50 volts. Now, applying Ohm's law, we can already do the math for this resistor right here. Let's call it R1 or whatever. And using Ohm's law, R1 is the voltage across it divided by the collector current. So the voltage across it will be VCC minus VC, and the current will be IC. So R1 will be 50, or 100 minus 50, which is 50, divided by 10 milliamps. And this gives us a value of 5 kilo ohms. So that's it, we already have the first value here. So as you can see, it's not that complicated. And then let's calculate this resistor as well. Let's call this R2. And now this is basically, this resistor sets the gain. So the gain of this amplifier, or AV, is approximately equal to RC over RE, or the collector resistor divided by the emitter resistor. In our case, it's R1 divided by R2. And in our case, AV is 10, which is what we are aiming for. So this already gives us the ratio between these two resistors. So once again, R1 divided by R2 equals 10, which means that R2 needs to be 10 times smaller than this resistor. So R2 will be 5K divided by 10, so R2 equals 500 ohms. And that's it. We have the second resistor value as well. Now let's see how we can move on with the analysis here. The base resistor, well, this one basically sets the bandwidth if nothing else limits the bandwidth here. So I don't know, let's go with 180 and see if it works or not. I'm not in the mood for doing the math, but this forms a low pass filter here with whatever capacitance we have in this node. So we can try this value and see if it works or not. And then we can move on to calculating the other values around here. So how can we proceed here? Well, first of all, we can do the math for the voltage that we have in this node, which is the emitter voltage, or VE. And this can be calculated once again using Ohm's law. So VE equals R2 multiplied by our current here. Now here we can apply another trick. We can assume that the beta of this transistor is really high, and if it's really high, then the collector current is equal to the emitter current. So we can assume here that this is the collector current as well, which means that VE is approximately 500 multiplied by 10 milli. So it's 10 times 10 to the power of minus 3, and VE will be approximately 5 volts. So we solved for this as well, and now we can move on to calculating these two resistors. Let's see. Well, here we have the base emitter junction, and the base emitter junction, when it's forward biased, has a voltage drop across it of around 700 millivolts. So we can say that VBE is 0.7 volts, which implies that the voltage in this node is VE plus VBE. So here we will have 5.7 volts. Now this will help to calculate the two resistors here, but we need some more assumptions before moving on. Let's give them some names. Let's say this is R3 and this is R4. And now in order to do the math here, I think it would be a good idea to take into account the base current. And we can calculate the base current, or at least approximate it, or find the worst case value. And that's because the worst case beta or HFE is in the data sheet. And HFE is greater than 50. This is what the data sheet says. So this means that if we have a collector current here of 10 milliamps, we can calculate the base current. So the base current IB is approximately equal to IC divided by HFE. And IB will be, let's see, this will be 200 microamps, which is 10 milliamps divided by 50. So in order for this amplifier to be stable, we need this current through the resistive divider here to be much larger than this, and the good value would be 10 times higher than this. So this current I3 will be it will be 2 milliamps, 10 times larger than the base current, in order to, so that the base current doesn't change the voltage in this node all that much. So using this assumption, we can move on with our analysis. And once again, assuming that the beta is very high and there is no current flowing in this node, which is essentially wrong, we can estimate this current as well, I4. And we can say that it is approximately equal to I3, and this is 2 milliamps as well. So if we know the current here, and if we know the voltage of 5.7 volts, then once again we can use Ohm's law to calculate this resistor. So R4 equals the voltage, which doesn't have a name here, 5.7 divided by 2 milliamps. And R4 is around 2.8K. And now we only have one more resistor to calculate. And once again, here we know the current and the voltage, so we just need to apply Ohm's law. So remember that we have a VCC equal to 100 volts, and here in the base we have 5.7 volts. So this gives us the current, this gives us the voltage across the resistor. So R3 equals 100 minus 5.7 divided by the same current of 2 milliamps. So R3 is approximately equal to 47K. And this is the complete design process for this amplifier. So let's recap. Since we want the output voltage to be around 50 volts peak to peak, we decided that VCC should be around 100 volts. Now, since VCC is around 100 volts, this gives us a VCEO of at least 100 volts, and this is how we decided that a transistor that has a VCO of 300 volts is good enough. Moving on to the bandwidth, which is another challenge of this project, we decided that our gain should be 10 and our bandwidth should be 10 megahertz. And this gives us the minimum transition frequency, FT, which is 100 megahertz actually. So this is how we chose the transistor, but unfortunately our transistor only has a transition frequency of 60 megahertz. Let's just hope that this is good enough. Moving on to how we chose the collector current. Well, the collector current is the collector current for which the transistor was specified in the datasheet, so we just went with 10 milliamps. And then the other concepts that we needed here was the VBE voltage, which is approximately equal to 700 millivolts. Then we needed the formula for the ratio between the collector current and the base current, so HFE is approximately equal to the collector current divided by the base current. This is also called beta, but whatever, beta is not really the same thing as HFE, but we digress. And then, having all these in mind, we can use Ohm's law and Kirchhoff's laws in order to calculate all the resistors in the circuit. So, if you really want to benefit from all this information, my advice would be for you to try to redo this design process. So, starting with a supply voltage of 100 volts, a gain of 10, and a collector current of 10 milliamps, try to redo the analysis and see if you get the same values for the resistors. The next step would be to try this out in LTSpice. So here it is, and in order to make sure that it's working, the first analysis that I will try is a DC operating point, and then I will look for the voltage here and at the collector current to see if the transistor is biased properly. So let's see. This is really inconvenient because this just gives us a table like so it's not the most beautiful way to show data, but it is what it is. So let's look at the output voltage. This is 52, so this is really nice. It's already looking good. So what about the collector current? So IC for Q1 is 9.5 milliamps, so this is pretty close already. Nice. So I think you can try other types of analysis as well. Let's do a transient analysis. To do this, we need a few periods. Let's say that 10 periods would be good enough, and then we need to set the input frequency to a really high value to make sure that it works. So 10 megahertz would be a good choice here, and we also have an amplitude of 5. Let's see what happens. Okay, and now we just click on the output, and this is looking pretty nice already. Let's see, the input is okay. So as you can see, there is plenty of gain even at 10 megahertz, so I think this is working. However, it's really hard to tell whether or not this is working properly, so you need some extra measurements here just to make sure that it works fine. So I would suggest adding some measurements for the peak-to-peak input voltage, as you can see here, peak-to-peak output voltage, and then you can do another measurement that divides those two in order to get the gain. And also, I think it would be a good idea to have a look at the THD, so you have some Fourier analysis too. So this is looking at the THD of the output to make sure that the amplifier doesn't distort too much, and then you have to drive it. You can actually overdrive it, or at least try more simulations until you reach the limit of your amplifier, so that you can see how much output swing can you get without without getting horrible distortion, basically. So these are the things that you need to look for. And on top of this, you also need to do an AC analysis and look at the bandwidth. So let's do this really quick. AC analysis, okay, run, and then you have to look at the bandwidth at minus 3 dB. So let's see if the gain is okay. Okay, our initial gain is around 17 dB, and we have to look at minus 3 dB from that. So let's drag this until the difference is 3 dB. We can read the difference here. Okay, we have minus 3 dB around here, and the bandwidth is around 8.3 megahertz. So I would say it's not that bad, actually. I think this is worth trying because it could work. In order to implement this, of course, you need to take the pinout of the transistor into account. So this is in the datasheet, and in the case of these transistors, it is ECB if you hold it like that. And here's what the circuit looks like. It looks terrible, honestly. It looks like a complete mess, but I think it's going to work. Actually, I did try it out, and it looks different from what it was on paper, because I didn't have the exact resistor values in my junk box, and also I had to reiterate a few times to get the collector voltage to be 50 volts. So let's try it out. And here it is. As you can see, it's a complete mess. The amplifier is connected in the circuit right here. You can barely see it, and to make things worse, everything is connected with alligator clips. So you should never ever do this at 10 megahertz, but let's give it a try anyway. We're just having fun here. This is the power supply for the whole thing. It's powered from an isolated variac, and this is a rectifier, filter capacitors, and so on. This is the converter board from the previous video, which is basically Alan's circuit, and here is the horizontal deflection amplifier on a breadboard. Let's do some basic tests before giving it a video signal. On this multimeter we have the collector voltage once again. I did my best to get it close to 50 volts. And we have around 44. I think this is good enough. We need to keep an eye on the collector current as well, so here it is on a different multimeter. Okay, not really 10 milliamps, but it's 13 milliamps. I would say this is good enough. And now is the moment of truth. Let's see if we get better video or not. Are you ready? 3, 2, 1, fire! Oh, we have something. And it's negative. Oh man, I forgot about this. This is an inverting amplifier, so we get negative video. Oh man, but it has higher contrast. You know what? These cameras used to have those silly effects, and I think it's able to invert the video in camera. Let's see. Haha. There we go. The video is now inverted, and whoa, it's so much better. I cannot believe it. Here it is. Here I am. The contrast is huge, actually. It looks really good, and you saw how messy the circuit is. I mean, I didn't even try to assemble it properly, and we still get a better picture, which is so nice. I love it. Here it is. As you can see, the picture is much brighter. It has much better contrast, but it's not really high definition, okay? So this is we definitely have room for improvement there, but we've made some huge progress. What do you think? Since we are aiming for a bandwidth of 10 MHz, I think it's a good idea to measure the bandwidth as well. To do this, I connected the amplifier to this signal generator, and I'm going to apply some test voltages in order to see what the gain is. So let's start with the low frequency. So for the low frequency gain, I'm going to apply a sine wave at 10 kHz and 1 volt peak to peak. On the oscilloscope we have the output on the second channel and the input on the first channel, and as you can see we have around 12 volts at the output, and since we have 1 volt at the input, this implies that the gain is 12. So now we have to find the minus 3 dB point. To do this we multiply 12 by 0.707 and we get a value of around 8.4 volts. So we need to increase the frequency until we reach that point. Let's see. Let's try 1 megahertz because we're optimistic today. And we are way below our 3 dB point. The output voltage dropped to 5.4. So unfortunately the bandwidth is really low. Let's try 600 kilohertz. 600 kilohertz, okay. This is still too low, so we need to reduce the frequency. How about 500 kilohertz? And at 500 kilohertz the voltage is close enough. We are aiming for around 8.4, so this means that our bandwidth is only 500 kilohertz, unfortunately. The possible explanation for this, except for the messy wiring, is that I neglected the capacitive loading of this amplifier. So this is the capacitance that we see on the input of this oscilloscope. So this is the capacitance that the amplifier needs to drive, which is huge for this bandwidth. To test this theory, I disconnected the oscilloscope and the wires, and the bandwidth increased, but it only increased to 1.45 megahertz. So another test of this theory is to once again use LT-Spice. So I added the measured capacitive load here, and I want to rerun the simulations to see what we get. And as you can see, the bandwidth is really low, so let's measure it. And as it turns out, the bandwidth is really low. So here it is, we are at around 3 dB, and we only get a bandwidth of around 20 kilohertz. So as you can see here, I tried various compensation schemes. So I tried peaking coils, I've tried emitter bypass capacitors, and they can increase the bandwidth to some extent, but the frequency response is nowhere near linear, so I don't like this solution. I tried another topology as well, which is a cascode, and this one distorts like crazy, and it also has a really low output swing, so it's not the best solution. And finally, something that seems to work better is the initial amplifier plus an output stage, which is a totem pole output stage. Once again, this is basic. It just uses 2 diodes for biasing the transistors, and the bandwidth is a lot better. Let's put a proper capacitor here and redo the simulation and see what we get. So now you have a side-by-side comparison, and as you can see, this one is doing a lot better, even though it's far from 10 megahertz. So let's measure the bandwidth once again. Let's go to the minus 3 dB point, which is somewhere around here. And as you can see, the bandwidth increased a lot. Now we have around 660 kilohertz. So I made this one on a breadboard, and here it is. This is the common emitter amplifier, and this is the push-pull stage. Let's see if it works. So here's the moment of truth once again. 3, 2, 1, fire! And yeah, I think it looks better. Let's give it more intensity here. Nice. I think the image is a little bit sharper. So we probably have a higher bandwidth here. What do you think? Maybe when I edit the video I will add a comparison so we can see them close to one another. Yeah, let's measure the bandwidth once again. So it turns out we have a significantly better bandwidth. The bandwidth is 1.6 megahertz. So this is more than triple the previous bandwidth. However, the bandwidth is far off from the simulation, so I think we're missing something in LT Spice. Anyway, this is definitely an improvement. Now, just before I wanted to wrap this up, something really interesting happened. I went live on TikTok and I complained about the bandwidth of this circuit being too low. And one of the viewers came up with a really interesting proposal. So they said, why don't you use a TDA 6108? Because this one is a triple video output amplifier and it should work in your application. And at first I was really skeptical, and I thought there is no way to find it because it's obsolete. However, I got really lucky. Here they are. Actually, I managed to find a few of these at a local electronics store, so I ordered them, and even though they are obsolete, I managed to get around 10 of these, and we can experiment with this as well to see if we can get away with a very simple circuit instead of all this mess that we've made so far. And here it is. It doesn't get much simpler than this because we only have the IC and the decoupling capacitor. So this is powered directly from 100 volts. We just feed it the input signal and connect it to the CRT, and that's about it. And we also have to bias it, so it needs a few volts of positive bias at the input in order for the output to stay at around 50 volts. And it has a gain of 81. It's a fixed gain amplifier, and it's also an inverting amplifier, so it's doing pretty much the same thing as our circuit from before. Let's see if it works. So this is it, TDA 6108. 3, 2, 1, fire! Oh, it works. It definitely works, but the contrast is huge and it looks terrible. Let's see if we can adjust it. So we need to dial it down from our converter board here. That's because this has a ton of gain and the contrast was all the way up. What about this? It looks weird. I think it's not biased properly. Let's try to bias it. Okay, this is really touchy as well. This is so strange. So this is biased from the video amplifier on the converter board, and as you can see, the bias is really touchy. This is saturated. Now it's saturated again, and I think it works best somewhere around here, but we need to reduce the contrast once again. It's hard to adjust it. I think the amplitude is just too much for this. Maybe, yeah, we really need to be patient when biasing this. How about this? So yeah, we have so many adjustments here that I don't know what the adjustment procedure for this should be, because we can adjust the intensity on the oscilloscope, and then we have a brightness and contrast on the converter board. So here it is. I'm not sure which one does better, but this could be sharper. It looks like it has lots of detail, and it's definitely the simplest circuit. So it doesn't get much simpler than this. It's just an IC and a decoupling capacitor. Once again, I think we need to look at side-by-side comparison. I'm eager to see the video when I edit this to see which one performs better. The results are really interesting. The bandwidth of the TDA amplifier is 2.3 MHz under load, and interestingly enough, if we disconnect everything from the amplifier, we get a bandwidth of 6 MHz. So this is by far the widest bandwidth that we managed to obtain. And in the end, as a final party trick, I just couldn't help myself, so I bought one of those cheap HDMI to composite video adapters, and I turned this vacuum tube oscilloscope into an HDMI display. So here it is as a third monitor to my computer, and we are on the Void Electronics YouTube channel scrolling through the videos. So yeah, I thought this was really fun. Unfortunately, the video bandwidth is not good enough for quality picture. You can barely read the text and so on, but it definitely works, and I think it's a really fun thing to do. So what's left here is just to turn everything into a PCB. So the video amplifier for the vacuum tube oscilloscope should become a PCB with a boost converter or something like that, and then I will also change something on Allen's circuit, and I would like to add some adjustments there for vertical size, horizontal size, and also vertical position and horizontal position, so that the circuit will be more flexible and it will be able to accommodate more oscilloscopes. So congratulations if you had the patience to watch this video until the end, and I will see you next time. Bye.